Welcome to today's Explainer. We're diving straight into a totally brilliant state-of-the-art generative AI architecture called ScrapMem. We're looking at a fascinating paper that attempts to solve one of the absolute most frustrating limitations in AI today, which is how on earth do we give an AI long-term memory without completely overloading its storage capacity?
So let's get right into the core problem. We all want the AI agents living on our phones and laptops to, actually remember us, right? If you tell your AI about your dietary restrictions, your favorite vacation spots, or, say, a project you've been working on for 3 solid months, you want it to just know that stuff seamlessly. But here's the catch. Our personal edge devices have highly limited storage. Taking all of your daily texts, videos, and photos and trying to make sense of them is just computationally exhausting.
Here's how we're going to break it down today. First, the AI memory bottleneck. Then, how we're inspired by human brains. Third, building the digital scrapbook. Next, the power of forgetting. And finally, some incredible state-of-the-art results.
All right, let's kick things off with part 1, the AI memory bottleneck.
Before ScrapMem came along, engineers generally relied on two, honestly pretty flawed paradigms to give AI memory. The first one is parametric memory. This is basically baking the information directly into the model's weights through fine-tuning. But the issue? It's something called catastrophic forgetting. As the model learns new things, it literally overwrites and destroys the old things. Not great. Then you have retrieval-based systems, but they face a really interesting hurdle. They struggle to align mixed media. They have a super hard time taking, say, a text message, a photo of a receipt, and a voice memo, and combining them into one unified logical space. Ultimately, these traditional methods just don't scale for personal devices. Storing thousands of photos, videos, and texts imposes this absolutely massive memory overhead. When you try to feed all of that raw multimodal data into an AI's finite context window, it just chokes. It simply can't perform long-range reasoning over the timeline of your life because the data is too heavy and way too fragmented. The researchers realized they needed a radically new, super storage-efficient solution.
Which brings us to part 2, inspired by human brains.
So, to fix this hardware issue, they looked at nature's blueprint. Notice how our biological memory actually works in 2 stages. First, our hippocampus acts as a fast learner. It rapidly binds raw, multimodal experiences, like scenes, context, visual cues, all together into a single episodic memory. Then, over time, our neocortex takes over for slow learning, gradually consolidating those transient memories into stable, structured, long-term knowledge. The researchers looked at this and thought, wait, we can mimic this exact process using a digital scrapbook analogy, basically binding raw data into pages and then gradually letting them age.
Moving right along to part 3, building the digital scrapbook. ScrapMem completely flips the script on how data is actually stored. Taking a cue from recent findings in vision language models, ScrapMem doesn't store your raw text, code, or data logs as massive text files. Instead, it treats your data as visual scrapbook pages. It takes all those mismatched, heterogeneous records and renders them into a single image. Now, why do that? Well, and this is kind of wild, treating text and data as an image slashes token consumption by nearly an order of magnitude. It's actually about 10 times more efficient for the AI to process a dense image of text than the raw text itself.
To make this work, ScrapMem uses a really slick 3-step pipeline. First, it aggregates all your temporal data, say literally everything you did on a Tuesday, into one cohesive visual scrapbook page. Second, it runs optical perception tools, like optical character recognition and vision encoders, to effectively read that visual page. And third, a large language model steps in to extract semantic nodes. This is basically the AI pinning down the core entities, the key events, and the most vital relationships between them.
Now focus on how those extracted nodes are actually handled. ScrapMem doesn't just toss them into a pile, it organizes them into an episodic memory graph, or EM graph for short. Think of it like a giant puzzle. Visual and semantic nodes are linked together into EM paths, mapping out cause and effect over time. For example, a path might link a node for fever to a node for doctor visit and finally to medication. This structure is a total game changer. It allows the AI to perform complex multi-hop reasoning across your entire history, rather than just endlessly searching for random keywords.
And that brings us to part 4, the power of forgetting.
Here is the truly counterintuitive hook. To make the AI better, it actually has to forget. The researchers introduced a mechanism called optical forgetting. Now, this doesn't mean the AI just abruptly deletes old files when its hard drive gets full. Instead, it systematically blurs them. It applies a time-dependent lossy transformation.
Basically, as time passes, the visual resolution of those old scrapbook pages progressively degrades. The trivial, unimportant background details fade away, exactly like an old photograph fading in the sun. This saves a massive amount of storage space. But crucially, because of that EM graph we just talked about, the core semantic structure, the actual meaning of the memory, is perfectly preserved.
And if you're sitting there wondering, wait, doesn't blurring the AI's memory ruin its ability to recall facts? Well, the data shows otherwise. The researchers tested multiple levels of this visual fading, from a very soft degradation all the way up to an aggressive constraint where memories fade much faster. But even under intense visual fading, the AI's retrieval performance remains incredibly robust. It turns out it doesn't need pixel-perfect high resolution to remember your life, because those causal EM paths act as an incredibly stable semantic backbone.
Finally, let's wrap up with Part 5, State-of-the-Art Results.
By allowing the AI to organically fade old visual memories, ScrapMem achieved a massive 93% reduction in total memory storage. I mean, just think about that for a second. The amount of space required to store long-term multimodal memory was cut down to a mere fraction of what standard systems require.
You can clearly see this dramatic shift in the efficiency data. The original raw data baseline was taking up over 4,300 megabytes of storage space. But with optical forgetting enabled, ScrapMem plunges that footprint down to just under 300 megabytes. And the kicker? It achieves this 93% storage reduction while still retaining over 90% of its peak performance. It's honestly a masterclass in efficiency.
The raw numbers on the multimodal benchmarks are just as impressive. ScrapMem hit a brand new state-of-the-art join-at-10 score of 51%. It easily beat out the previous best retrieval augmented system, which scored 48.6%. It also became the only system tested to exceed a 70% score on recall at 10. By organizing memory like a human brain, binding it like a scrapbook, and letting the useless details fade away, ScrapMem completely proved to be fundamentally superior at retrieving long-term, complex, multimodal knowledge.
So, the crucial point we are left with today is this. We've spent years trying to make machines perfect, striving for infallible, infinite, pixel-perfect retention. Yet, this entire breakthrough was achieved by mimicking one of our perceived biological flaws. If we're now engineering neural networks to purposefully degrade and forget information exactly like our own brains do, what other deeply human quirks will become the secret to the next breakthrough in AI? Thanks for joining me for this explainer, and I really hope this leaves you with something fascinating to think about.